Hi everyone, I'm David Woodruff from Carnegie Mellon University, and today I'm going to be talking about adversarially robust streaming algorithms. Okay, so this is a talk based on a few works that are joint. One is joint with Omri Ben Eliezer, Rajesh Jairam, Alain Yogev, and the other is based on joint work with Samson Joe. So let me start by describing what the streaming model is. This is a model for formally capturing extremely large data sets. For example, internet traffic, financial transactions, sensor networks, and so on. And typically for such data sets, it's very expensive to make more than one pass over the data set. For example, if it's network traffic, it might actually be impossible to make more than one pass unless you explicitly store the data somewhere. So you typically want one pass and very low memory algorithms. Imagine having such very large traffic going through a very limited internet router. It needs to store a summary or a synopsis of what it sees because it can't afford to store the entire data set. So formally, this is modeled by a stream of a polynomial and n number of updates to a large underlying vector x in R to the n. Okay, so typically you have some object and you can model it as a vector. And at times t equals 1, 2, and so on, you receive updates to this vector. So an update has the form I sub t comma delta t, which causes the change. The ith coordinate of x increases by delta t. Okay, so the new value is its old value plus delta t. Typically, initially, this vector x is also all zeros. Okay, so you're receiving these additive updates to the coordinates of x at different times. There are various streaming models. For example, if at all times these changes delta t are non-negative, this is called the insertion-only streaming model. Okay, so maybe you're looking at number of packets sent from one IP address to another that corresponds to an entry in a vector, and this number is only increasing in time. However, there are other models as well where the delta t's can be positive or negative, and this might be useful for measuring the difference in how many packets are being sent from a source to a destination IP at different times. Okay, so as I said, the algorithm needs to be low memory, so it stores a small sketch of the data, much smaller than n bits. Okay, it can't afford to store this entire vector. And at any point in time, the algorithm might be asked to compute a function f of x, or to approximate a function value f of x using this small amount of memory. Okay, typical functions of interest include, for example, f sub 2, which is the squared Euclidean norm of x. This is the sum of the squares of the entries of x. Or, for example, the number of distinct elements, which is denoted f sub 0, is just the number of coordinates I such that xi does not equal 0. Okay, sorry, this f2 was the Euclidean norm, f0 was the number of distinct elements. And to give you a flavor of how algorithms work in the streaming model, let me describe how you might estimate f2. Okay, so here you'd like to output an estimator f2 tilde, for which f2 tilde is at least 1 minus epsilon times f2, and at most 1 plus epsilon times f2. Okay, so it's a 1 plus epsilon relative error approximation. Recall f2 was the squared Euclidean norm. And the way to do this is to choose a random wide and fat matrix S, and all the entries of S are plus or minus epsilon. Okay, so you can write S as epsilon times a matrix of plus or minus 1s. And all the entries plus or minus 1 are random. They could be truly random, but then it might be expensive to store this matrix S, and you want a low memory sketch in the streaming model. And I do want to mention that this matrix S is large. Okay, so it's roughly 1 over epsilon squared. Remember, epsilon is the approximation you're looking for by n. N is this length of the vector. So you can't afford to store this matrix S. It's already bigger than the n-dimensional vector. But typically, these S can be generated pseudo-randomly. Okay, so for example, the entries of S can be 4-wise independent, meaning actually that S can be represented with a small pseudo-random seed using only order log n bits. And in the stream, what you do is you maintain S times X. Okay, so X is this underlying vector. And all you're doing is computing the matrix vector product S times X. Okay, so given an update, X sub IT goes to its old value X sub IT plus delta T. It's very easy to update the sketch. S times X goes to its old value S times X plus delta T times the ith column of S. Okay, so the fact that S is linear and is random, so it doesn't depend on the underlying vector X, allows for these updates to be maintained in the stream. You just add a delta T multiple of the ith column of S to your sketch when you see the update to the ith coordinate of X by delta T. Okay, and at the end of the stream, the estimator is extremely simple. You just output the squared Euclidean norm of this much shorter vector S times X. It's only 1 over epsilon squared dimensional. Epsilon might be 10% or something. So this would be a 100-dimensional vector versus an n-dimensional vector, which could be huge, maybe 2 to the 32 or something. So the point is S times X is a much smaller vector. You still output its Euclidean norm, and you can show the expectation of the squared Euclidean norm of S times X is the squared Euclidean norm of X. And the variance is also order epsilon squared times the square of the expectation. And therefore, by Chebyshev's inequality, you can show that you output a good 1 plus epsilon approximation with decent probability. Okay, and the point here is that the number of bits of memory is only log n over epsilon squared. Okay, so you need order log n bits to store this matrix S pseudo-randomly. And you also have this vector of dimension 1 over epsilon squared, S times X. And each entry can be stored with log n bits of memory, assuming the entries in the stream can be stored with log n bits of memory. Okay, so it's a simple algorithm. And typically, as I mentioned in data streams, you're interested in tracking algorithms. So what you'd like is if you let xt be the stream vector after updates 1 through t, then you'd like the algorithm to output at time t an estimate rt, which is within 1 plus or minus epsilon of the function value f of xt. You'd like this to happen at all times t. Okay, so the model in the streaming model, the setup for the streaming model is that there's some data. I've drawn it here as a sort of a cylinder here, this data source. It generates IT delta t, this update to the ith coordinate. Here you are on the computer. This is a streaming algorithm, and you output RT, the response. Okay, and then IT plus 1, delta t plus 1 comes along, and you output the next response, RT plus 1. Now, interestingly, in this model, this data center, the thing that's generating these updates, it doesn't see your responses, RT, RT plus 1, and so on. And that is the model that has been around for a long time. In classic streams, the data is fixed before the algorithm starts. Future data does not depend on the outputs, RT. And somewhat surprisingly, before this work, there were no known guarantees for streaming algorithms where future data often depends, is allowed to depend on your past responses. And that's what adversarial streams model. So here, the adversary controls the stream updates. So it gets to see your responses, RT, then gets to choose the next stream update, IT plus 1, delta t plus 1, and so on. Okay, so this can be modeled by a 2-player game where there's an adversary here. It doesn't necessarily need to be an adversary. I mean, you can imagine there are lots of situations where future data depends on past data. And for example, if you have a stream of financial transactions and you're making some prediction to buy a stock, maybe this influences the future stream of transactions. So it's drawn here as an adversary in any case. And this adversary generates I1 delta 1, and now it gets to see the streaming algorithm's response, R1. Then it generates I2 delta 2, it sees the streaming algorithm's response, R2, and so on. So the point is the adversary gets to use the past responses to generate its future updates to the stream. Now, the past responses depend on the underlying randomness of the streaming algorithm. And so there's a question, if I'm getting future updates that depend on my own randomness, then does my algorithm still work? Okay, so the goal of the adversary is to make the algorithm fail to output an epsilon approximation at some point in time, meaning that the response RT should not be within 1 plus or minus epsilon of f of xt. The goal of the algorithm, of course, is to have all the responses be correct, be 1 plus or minus epsilon approximations. And for this talk, though there is some recent work on what's called the white box adversarial model, for this talk, the adversary has unbounded computational power, okay, and knows the entire history of responses at a time t. Okay, this recent work I mentioned on the white box model often places computational assumptions on the adversary that's not too powerful, and allows even for the adversary to see the internal workings of an algorithm. But for this talk, we're just going to say the adversary receives the responses. Now, deterministic algorithms are naturally adversarially robust because they work on any input, even adversarially chosen inputs. However, most streaming algorithms provably must be randomized to obtain a small amount of memory. Okay, now, you can look at classic data stream algorithms. One is called the Alon-Matthias-Szegedy or AMS sketch for estimating F2, which is the algorithm that I presented earlier. And you can show that these are not adversarially robust, even in this restrictive streaming model where all the updates are non-negative. Okay, there's a simple attack on this. And so the idea is we need new algorithms. Okay, so we're going to have to, even this attack, what it roughly amounts to is, you feed in an input, and you look at, you get the actual squared Euclidean norm of the output in this model, and you can check if it, if it increased by slightly less than it should, or by slightly more, and you can find columns of the sketching matrix S that are correlated with each other by doing this. And once you've done that, if you find a bunch of positively correlated columns, then you can plant a very adversarial vector which is only supported on those columns and blow up the norm, and that's how you fool these kinds of algorithms, or shrink the norm. So the main result of this first work with Ben Eliezer, Jairam, and Yogev is that we give two generic methods to transform any streaming algorithm A into an adversarially robust streaming algorithm A prime with only a mild space overhead. We call these sketch switching and computation path methods. Okay, now these two methods are useful in different regimes of parameters. So sketch switching is particularly useful for exploiting algorithms which provide tracking better than one shot plus a union bound over all time steps. Okay, what I mean by that is, oftentimes you develop a streaming algorithm which is good at any particular time. And if you want it to be good at all times in the stream, what you can do is boost its failure probability by repeating it multiple times in parallel. And once its failure probability is reduced to be significantly small, you can union bound over all times in a stream. But there are algorithms that avoid that union bound, and sketch switching is particularly suitable for obtaining more efficient tracking algorithms and adversarially robust ones. Computation paths, similarly, are useful for exploiting algorithms with a better dependence on the failure probability delta than a typical multiplicative log 1 over delta. And there is some relationship between these two methods that I won't get into, but computation paths can typically result in better update time because of that, though maybe worse log factors than sketch switching in the memory. Okay, so in order to formally state our results, for a function f from Rn to R, we define the epsilon flip number, lambda sub epsilon of f, to be the maximum number of times a function f can change by a factor of 1 plus epsilon after poly n updates in the stream. Okay, and just to give you a flavor, as I said, this vector x is typically initialized to 0. And if we look at f of x being the LP norm to the p, which is just the sum of p powers of the absolute values of the entries of x, then initially the function value is 0 because the vector x is 0. And the thing is, you can only, since at the end of the day, all the entries are integers bounded by polynomial in n, that's the streaming model. Well, the number of times the function changes, in this case, it's only growing, changes by a 1 plus epsilon factor is log base 1 plus epsilon of poly n, which works out to order 1 over epsilon log n. Okay, so think of the flip number as a quantity which is roughly 1/epsilon log n. And okay, so let me tell you now, with that notation in mind, what sketch switching roughly does. So it keeps multiple, roughly lambda, this flip number, number of independent sketches concurrently. Okay, so it generates lambda sub epsilon sketches at the beginning, and it's running each of these sketches in the background on the underlying vector. However, it's only using the output of one sketch Si at a single time. Okay, so and once the so Si is outputting something, and once the estimate that Si outputs RT changes by a 1+epsilon factor, then information about the sketch Si is compromised. Its randomness is compromised. So we throw it away and we start monitoring the next sketch Si+1. Okay, so the idea is, I'm going to have these sketches, and at some point in time, I reveal the output of the ith sketch. Okay, and Si+1 has been running all this time on the underlying vector, but no information has been revealed about it so far. Okay, and now we're going to keep looking at the output of Si+1, but we're not going to be revealing it to the adversary. But we're going to keep checking, has it grown by a 1+epsilon factor from the output that we revealed from Si? If it hasn't, we keep using the old output of Si. And at some point we notice, oh, shoot, the output of Si+1 has changed by a 1+epsilon factor over what we've previously revealed to the adversary. So we now reveal that to the adversary, but now the output of the sketch Si+1 has been compromised, so we throw it away, and now we fix the output of Si+1, and we're looking at the output of Si+2, not revealing it to the adversary until it actually changes by a 1+epsilon factor, and so on. So this is why you need roughly flip number of different sketches, because this is how many times your function value is going to change. And also, you see that intuitively why this is secure. I'm not going to give the formal proof, but intuitively why the adversary can't break the algorithm is that it has no information about the next sketch until it's too late. You're no longer using that sketch. Computation paths, on the other hand, this other general framework, what the idea here is that you just take any existing streaming algorithm and you just change its failure probability by making it much smaller. So you take the failure probability delta and you instead replace it with delta times n to the minus flip number. Okay, so the idea is you're going to make your flip number so small that even revealing outputs of the algorithm to the adversary as you go is not going to compromise the internal randomness. Okay, so the idea here is that you're only going to need to change your output flip number of times. Now the stream length is only poly n, and typically for these problems the output is only order log n bits at any point in time, or even fewer if you're rounding it. So the number of possible computation paths, what I mean by that is, you're going to reveal an output at some point in the stream, and that output has some value. Then you're going to reveal the next output at some point in the stream, that output has some value. And you can think of this as a tree that's growing for all possible times in the stream and outputs you're going to reveal. Well, the depth of this tree is only a flip number. And the branching factor is poly n. So there's n to the order flip number of possible trees you can generate. And if you just set this failure probability delta to be small enough, you can simultaneously union bound over all of them. So no matter what happens, whatever path the adversary chooses, you're going to be correct. Okay, so that's the idea. And you can see in both cases that roughly the overhead that we get for being adversarially robust is flip number, right? That's the number of sketches, additional parallel sketches we need to run for sketch switching. And for computation paths, typically you have a log 1 over delta dependence in your streaming algorithm. And so you're going to get, your sort of this n to the minus flip number, you're going to get log of that. It'll be a flip number overhead as well. These can be formalized. So these are the two informal theorems that I have on the slide, which tell us that, the first theorem is using sketch switching, and the space that you get, let A be any algorithm which epsilon tracks some function. Then there's an adversarially robust algorithm A prime for epsilon tracking the function using space, which is the flip number times the space of the non-robust algorithm A. The other theorem on the slide, which is based on computation paths, is you let A be in the algorithm which epsilon tracks this function with some probability 1 minus delta and some space of A delta. Then consider this new algorithm A prime, which has space of the old algorithm A with delta prime being the old delta times n to the minus flip number. And that's the adversarially robust algorithm A prime. Okay, so its space grows by replacing this delta parameter with this new delta parameter. Yeah, so that's our main result here for sketch switching. I've just put the theorem here that I just said. There's a formal algorithm here that I'm not going to have time to get into, but you do initialize these independent sketches. You can, if you're watching this, you can pause it here and try to digest this, but you initialize these independent sketches. They're not 1 plus epsilon approximations, 1 plus epsilon over 10 approximations. You start by monitoring the first sketch, I equals 1. The initial response is 0. Typically, these functions you're computing are 0 when the vector is 0. And you just check, if the estimate your current sketch SI is not close enough to your old response at 1 plus or minus epsilon of the response in the previous time step, then you increase I by 1, and so you start monitoring your new sketch, and your new response is the estimate of SI, and you throw away SI because its randomness has been compromised. So it's just formalizing what we did. There's some fudging of the epsilon factors to make it work to get an overall 1 plus epsilon approximation. Here's our main result for computation paths, just repeated here. The nice moral here is that you can just take an existing streaming algorithm and change its failure probability. Okay, so you don't need to change the code. It's just readjusting parameters. And the proof is similar. You only need to change the output roughly flip number of times, and there are not that many possible streams the adversary can create, union bound over all of them, as I said before. Okay, so we get lots of results for adversarially robust streaming for things like estimating distinct elements, FP estimation, which is these LP norms, the P, heavy hitters, finding items that occur very frequently in the stream, estimating entropy. It's useful for things like denial of service attacks. You can see here on the slide the non-adversarial memory requirements, and you can see the corresponding adversarial memory requirements. And there's only a mild overhead. Okay, roughly for many of these problems, it goes from quadratic in 1 over epsilon to cubic. There was very interesting follow-up work of Hasidim, Kaplan, Mansour, Matthias, and Stemmer that used differential privacy in this context. And it was able to improve these bounds from roughly cubic in 1 over epsilon to roughly 1 over epsilon to the 2.5 for many interesting problems. More generally, the blow up in the flip number is square root flip number as opposed to linear in the flip number. There was also follow-up work which introduced the concept of difference estimators in the data stream model, work with Joe. And we improved these bounds, 1 over epsilon cubed, 1 over epsilon 2.5, we were able to get the optimal 1 over epsilon squared, which matches the dependence on epsilon in the non-robust setting. And has applications to things like sliding windows and so on. Roughly the blow up in flip number is epsilon times the flip number. It's since many of these problems the flip number is 1 over epsilon. This means the blow up doesn't even depend on epsilon. It's logarithmic. As I said, it's optimal in that sense. And it resolves some open questions, Braverman and Ostrovsky for sliding window model for FP moment estimation, these difference estimators. So I have all the results here. Again, as I said, it's roughly a quadratic dependence in 1 over epsilon for many of these problems. Even more follow-up work. Kaplan, Mansour, Neeson, and Stemmer exhibit a problem in the insertion-only model where this square root flip number dependence is necessary. For appropriate setting of parameters, this gives an exponential separation for robust and non-robust algorithms. And interesting work of Matthias, Cohen, Schechner, and Stemmer is able to combine these difference estimators in this work that I have with Joe, together with this differential privacy work that I mentioned earlier, Hasidim et al., and get a square root epsilon times flip number dependence. That's all I wanted to mention. There's a lot of exciting work on this adversarially robust streaming model for graph problems. I mentioned this white box model where you reveal more than just the output, you reveal internal guts of the algorithm. And I think it's a very active area. And thanks a lot for your attention. That's all. Bye-bye.